Welcome to my new fifth video. Now we are going to do the second example in this course. So let's start. The example says that the magnetic structure of a synchronous machine is shown schematically in figure 2. So this is a basic figure of a synchronous machine. It has a stator and it has a rotor. Assuming that the rotor and the stator iron have permeability that goes to infinity, so the permeability mu is equal to infinity, find the air gap flux and flux density when we know that the current in the coil is 10 amperes, number of turns of the coil are 1000 turns. The air gap length, G, with small g, is equal to 1 centimeter, but 1 centimeter is 0.01 meters, and the area of the air gap here of one pole is 0.2 meters squared. 2000 centimeters squared is 0.2 meters squared. Okay, now here we have a synchronous machine. It has a rotor and it has a stator. And every machine, rotational machines, unfortunately have a small air gap. The good part of this is that we are assuming that the permeability of the stator iron core and the rotor iron core has the permeability of infinity, which kind of makes stuff easy. So the MMF, the magnetomotive force Ni here is produced the MMF. Now we have to calculate what is the flux in this machine. Well, the flux, if the fringing and the leakage are ignored, are neglectable, then the flux all around this machine is the same. Now, what is the direction of the flux? Well, these fingers are going to show the direction of the current, and this right thumb is going to show the direction of the magnetic flux density. But we are assuming that flux is not a vector, it's a scalar, but we always give him a direction of the we always make flux in the direction which is the same as the magnetic flux density. So current is going to produce magnetic flux that is going up. It makes a full circle and it comes back. So it goes here into the circumference of the stator through the air gap and it comes back. So we can we can make a schematic for this magnetic circuit. So we have a magnetomotive force Ni produced over here. Now, first we have the resistance, the reluctance of the rotor. Now we have Now we have one reluctance of an air gap over here. Now we have the reluctance of the stator. And again here we have the reluctance of the air gap. So we have one more reluctance, and the flux is going in this direction. Now, because it says that let's take a so how do we calculate the flux? Well, the flux is equal to the MMF produced by this N times I, so N times I, divided by the series reluctance of these four elements. Now we have in series two air gaps, so I'm gonna write 2 RG. So this is, we have two air gaps, so this is the reluctance of one air gap multiplied by 2. Now we have plus the reluctance of the rotor and plus the reluctance of the stator. But if you remember the formula for the reluctance of the rotor and the stator, or reluctance, if you know, the basic formula for the reluctance is that it is equal to the length divided by the permeability times the area. So if we assume that that stator has a reluctance of infinity and rotor also, this becomes 0. So reluctance of the rotor and the reluctance of the stator is equal to 0. So we don't write it. Now we can so the reluctance of the air gap is equal to length of the air gap times divided by mu 0 G, but multiplied by 2 because we have two air gaps in this magnetic circuit. This electrical machine has two air gaps, here and here. Oh, okay, it has here, but we assume that there is no flux leakages and fringing, so the complete flux goes right through here and comes back into its coil. Okay, so now the flux is equal to N times the current divided by 2 length of the air gap, which is equal to G, sorry, divided by mu 0 and AG. Now this is a double fraction, so this part here goes into the numerator. Now we have everything, and we are just gonna change these values into the specific numbers that are given in the example. So for N we have 1000, for the current we have 10 amperes, for the mu 0 it's 4 pi 10 to the minus 7 times the area of the magnetic pole is 0.2. Two times 0.01 meter, it's 0.02 meters. And we get that flux in the machine is equal to 0.13 Webers. Now it is easy to calculate the magnetic flux density, which is equal to, because the flux, magnetic flux in all this circuit is the same, we just have to divide this flux with the area of this air gap. So we are calculating the magnetic flux density in the air gap, and magnetic flux density also stays the same. That's equal to 0.13 divided by 0.2. And we get that the magnetic flux density is equal to 0.65 Teslas. So this is the solution for this example. Thank you for watching, and see you in my next video, where I'm going to do one more example. Then I'm going to show you the inductance of the coil, and then I'm gonna do more examples, and I don't know what comes next. So stay tuned.